In this video, we will give a short insight into the topics that we have covered so far, and using examples, how we can use our knowledge to further explain curves and surfaces. The study of curves and surfaces has been of paramount importance for a number of years, as they can be found in all areas of mathematics. Furthermore, they also have a number of wide-ranging applications such as graphic design, aerodynamics, and the understanding of geography. But first, how can we represent curves and surfaces mathematically? If we can answer these questions about curves and surfaces, we will be well on the way to understanding the properties of each curve and surface and why they are so important. So, for any given plane curve, we must consider each of these 4 points in turn in order to give us a better understanding of a curve and its functions. For example, if we take this plane curve, we can look at the 4 points that were mentioned earlier and see how we can use those to describe it. Before we can look any further at our curve, we must first ensure that it behaves well for all t in our domain. However, we can see that there is a self-intersection point, and thus it is not smooth at the origin. Hence, we need to restrict our domain to remove any of these points. So, to do this, we can look at the regularity of a curve. Using the arc length function, which tells us the length of a path on any given curve, we can then find the speed of a particle travelling along said path for any given time t. Furthermore, a curve is said to be regular if the speed is not equal to 0, i.e. the particle is not stationary. In this case, we can proceed to finding a unit speed curve. Using our curve, we can then find its speed and plot it against time t. Note though, at time t equals 0, the speed of our curve is also 0. Hence, to ensure the curve's regularity is maintained, that we need to limit the domain of time t. Furthermore, we can also see that the speed is not constant and varies in time. Finally, as the integral of the arc length function and thus the speed cannot be found explicitly, we cannot proceed with the unit speed, and thus we need to explore different avenues when we want to explain our curve. Simply put, the curvature measures how much a curve curves, i.e. it tells us how much the tangent is changing. For example, if we take a small circle and a large circle, the larger circle should have a smaller curvature than the small circle, as the larger radius of the circle implies that there are less changes in the tangent and vice versa. Looking at our curve, we can say that for small t, the tangent is constantly changing, i.e. the tangent has a higher rate of change. But as t increases, we can see that the rate of change of the tangent gets less and less. Therefore, we would expect the curvature to become smaller as t gets larger. Given our expression for the curvature, we would expect as time gets larger, the magnitude of our curvature to become smaller. Indeed, when you plot the curvature against time t, we see that as time gets larger, the curve spirals become larger, hence the rate of change of the tangent becomes less, and indeed the magnitude of the curvature becomes smaller.
Space curves lie in 3 dimensions. They are really useful in the real world. For example, we can use them to help us design roller coasters. We can consider the following curve. It's in 3 dimensions, so it's hence a space curve. The curve starts with a small coil and spirals out. Just as we did for the plane curve, we can calculate the speed. We again restrict the domain for the same reasons as before. We can also compute the curvature. From this, we can see that we have the same result. The curvature tends towards 0 as t increases. But will this curvature alone be enough to describe a space curve? Well, actually we need another piece of information, which is known as the torsion. In the case of plane curves, we only needed to consider the normal and tangent to the curve. But now that we're considering another dimension, we need another vector on our orthonormal basis. Hence, we introduce the binormal, which is perpendicular to the tangent and the normal. That is, it is perpendicular to the plane in which the curve lies. Now that we have this binormal vector, we can use it to find the torsion. The torsion tells us the curvature of the entire plane in the direction of the binormal. That is, it tells us how much the curve curves in 3 dimensions. For our example, we can see that the torsion is decreasing in time and is tending towards 0. What does this mean? Well, it tells us that the space curve is approaching a plane. In other words, the curve is getting flatter. If we look at our curve, we can see this is indeed the case, and the torsion is exactly what we'd expect it to be.
Surfaces are planes that curve in 3 dimensions. They can be used for many things in the real world, for example in architecture. Here is our surface. It self-intersects, therefore we have to restrict the domain. This is known as the Catalan surface. For the surface, we can plot the coefficients of the first fundamental form. From these, we can see that as E is equal to G, the lengths of the tangent vectors change by the same amount in the direction of U' and V', whilst there is also no change in the direction of U', V'. We can also plot the coefficients of the second fundamental form. Here, as E is equal to minus G, the length of the tangent vectors change by the same amount in opposite directions. A surface can be described using the principal curvatures, which are found using the shape operator A. The principal curvatures tell us how much a surface bends by giving us the maximum and minimum points. We can find the curvature of a space curve using our surface if a space curve lies on the surface. To do this, we can use the normal and geodesic curvature. The normal curvature is given by the principal curvatures, and theta is the angle between the tangent of the curve and the eigenvector of the shape operator corresponding to the principal curvature K1. This is Euler's theorem. So the principal curvatures are the maximum and minimum normal curvatures of all unit speed curves on the surface that pass through this point. Here we've plotted the principal curvatures of our surface, and from these it is clear to see that it is not defined at u and v equal to 0. So here we have k1 is equal to minus k2, and the mean curvature is therefore 0. As the mean curvature is 0, we have a minimal surface. Minimal surfaces have minimal area. These can be illustrated by soap films. As can be seen in the first image, instead of creating a cylinder shape, the film curves to minimise the area. This has been a brief overview of curves and surfaces, from plane curves to minimal surfaces. There is much more to explore.